Halvar, please take it away.
Yeah, good day. I have remarkably little to show. What I will just show is essentially how I used Claude Code and Gemini to optimize a little bit of PyTorch Python. In my case, I had, I'm somebody who has very little experience in writing PyTorch code. So I had used Claude Code to write a Python script for me that helps me visualize some things around the evolution of neural networks during training. For this visualization, I need to take a picture of 1024 by 1024 pixels and do a forward evaluation through that network, which is cheap to do on the GPU. But then also I need to take essentially a binary string consisting of which neurons are active and which neurons are not active for each of these pixels and hash that string, because I need to have a hash for the activation pattern for every pixel. I'll show in a bit why that is something I need. Anyhow, I had this script. It worked very nicely for small networks of like 50 neurons or 150 neurons or 200 neurons. As I tried training bigger networks and still visualize the training dynamics, this got to be way too slow. And as a result, I stared at the code, I did a little bit of profiling, and it became very evident that the problem was that forward evaluation of the network stayed on the GPU, but then PyTorch would helpfully copy the binary string of all the activations back to the CPU and then have the CPU hash things. Now, given that the string has a length that is linear in the number of neurons, as you scaled up your network, the string got longer and longer. But we have to do 1 million of these evaluations, so it got by a lot slower every time I increased the size of network. I ended up running an experiment where I had both Gemini and Claude Code side by side, and provided the following data or the following prompt to both of them. The Python script in this directory trains a fully connected leaky radio network on an input image and tries to reproduce it. It also draws pictures illustrating the boundaries of the polytopes generated by the creases that the radio creates in input space. Unfortunately, the code to generate the polytope visualization is slow, blah, blah, blah. I explain why this is slow. I ask it to speed up the computation, and I sketch out what sort of solution I would like. At this point in time, I had actually considered rewriting the entire thing in CUDA myself, but I had heard I may not need to do this because there's something called forward hooks in PyTorch that allow me to do what I want to do, which means not generating a bit string and then hashing it, but doing the hash as I'm doing the inference. But I had no idea how this actually works. So I tell the thing, I've heard that you can use PyTorch hooks, but I don't know exactly how. I give it a command line to run for the script, and what the output is. I tell it that the current visualization takes more than a minute, and we're spending a lot of this time on the GPU. And then I tell it, please do the hash calculation during the forward pass on the GPU, ideally without storing the activation vector in memory, and instead having a hash function that can be updated commutatively, so each radio unit can update the final hash while it calculates the forward pass. So I give it a sketch of what sort of solution I have in mind to make everything faster. I ask it to create a plan for improving, to implement the plan, and then to rerun the script with a specified command line, observing the speed up, like double checking whether you actually made things faster, and also whether it was made faster over multiple training steps. I also ask it to verify that the output image is identical to prior to the change, which is actually reasonably important. So I let both models churn. Turns out the models are actually reasonably good at doing Python profiling themselves and interpreting the results. So Claude one-shotted the example. Gemini initially did not, like the Gemini provided output did not generate the same visualization. So I had to tell it once more to essentially fix the output. What had happened is that Gemini had added some randomness into the hash generation, and by this screwed up the RNG state, and through this the outputs were different. And it all worked in the end, and the AI optimized version went from about a minute per frame to about half a second per frame. So the optimization step was a success. And that's pretty much all I have to say.
And we'll get rid of that noise. Thank you so much, Halvar. Really appreciate it. There was a question. Moon, do you want to take that over?
Yeah. So Guy in the chat is asking, how do you get the model to profile? How did you plug that in? I'm guessing you just let it choose its own profile or profiling method. Speed. I think we lost him.
Thank you. So the question is, actually the model itself will, like if you tell it, please use profiling to do it, Python has built-in profilers. So in my case, the model actually modified the script to enable profiling and then reran the script to get a profile and then interpret the profile. I would guess if you're running something like C++ code, I wouldn't be surprised if Claude Code and Gemini could just run the perf command line tool. As far as I know, they can run pretty much any bash tool that you instruct them to run. So yeah, I mean, it would be pretty interesting to see whether you can hook up a memory profiler and then have it optimize memory footprint and so forth. No framework. I used Gemini-CLI and Claude Code. I'm not an IDE kind of person. I do all my programming in a screen session on a remote machine. So just having one screen session with Gemini-CLI and one with Claude Code. What I end up doing is I check out multiple branches I check out the same repository. Every agent gets its own branch. And then I run them at the same time against them, and then I compare the branches, whether they get similar ideas or not. I do a fair bit of code reviewing before I commit anything.
All right. Thank you very much, Halvar. Really appreciate your time today.